Hello guys, in today's video we are going to talk about the need for multiple access protocol. Alright, first of all, reading out the statement, it says that if the link between sender and receiver is dedicated, then control layer is sufficient. However, if there is no dedicated link present, then multiple stations can access the channel simultaneously. Hence, multiple access protocols are required to decrease collision and avoid crosstalk. So basically, why do we need multiple access protocol is because uh, if there is a dedicated link between two computers, then of course there's no need for that, because only two computers are having the access to that particular link. However, if there are 3, 4 or multiple computers that are having access to that particular link, then any of those computers can send data simultaneously. Suppose if my computer and your computer are sending data to another computer, and somehow we just send the data simultaneously at the same time. Okay, now that of course is going to lead to collision. So that is why we do need multiple access protocols in order to use a single channel that is dedicated to more than two devices to use that channel more efficiently. This was about the need for multiple access protocols. Now moving to multiple access protocols. So basically there are three main types: random access protocol, controlled access protocols, channelization protocols. Now coming to random access protocol, it has four of its random access protocols, that is Aloha, CSMA, CSMA-CD, CSMA-CA. Okay, in controlled access protocols we have three of them: reservation, polling, token passing. And lastly, channelization protocol, we have FDMA, TDMA, CDMA. Now we are going to look at each and every one of them in detail. So let's move to the first one, random access protocol. Basically, in these, all stations will be having the same superiority. Alright, now what does this mean? First of all, just listen to what I'm saying. In this protocol, it's just kind of that there's a link between this link that 4, 5 or more than that computers are using, and any of that computer can send its data at any time as it wishes. So there's no one to tell that computer that you don't have to send your data at this very moment because the channel is busy, or there's no one to authorize that computer. So what basically is happening is that it's just basically that there's sort of no particular rules defined to maintain the efficiency. Okay, coming on to the statements, in this all stations have same superiority, that is, no station has more priority than another station. Any station can send data depending on medium's state, that is idle or busy. Of course, if the medium is already busy, no computer is going to send the data. However, if it is ideal and 2 computers, 3 computers, 4 computers are sending the data simultaneously without any of the restrictions, then of course it's going to be a collision. In random access method, each station has the right to medium without being controlled by any other station. This is what I told you earlier. If more than one station tries to send it means if more than one station tries to send, there is an access conflict, collision, and the frames will be either destroyed or modified. It simply is saying that the integrity of the frame won't be stabilized or won't be maintained. To avoid access conflict, each station follows a procedure. Okay, when can the station access the medium? What to do if medium is busy? How can the station determine the success or failure of transmission? Lastly, it says, what can the station do if there is an access conflict? Okay, so the second type we talked about was controlled access protocols. In random access protocol, basically no computer has No computer was needed to be authorized by any other computer in order to send data. Computers in random access protocol send data by their own free will. They are free to send data whenever they want. Okay, but in controlled access protocol, the station consults one another to find which station has the right to send data. A station cannot send unless it has been authorized by other stations. Okay? Channelization protocol. Channelization is a multiple access method in which the available bandwidth of a link is shared in time, frequency, or through code. Okay, between different stations. So this was basically about, I'm sorry guys. So this was basically about what random access protocol, controlled access protocol, and channelization protocol is on the bigger picture. Now we are going to look into them in quite a detail. First of all, looking at the first very protocol of random access protocol, that is Aloha. Aloha is a random access protocol. It was actually designed for wireless LAN, but it is also applicable for shared medium. In this, multiple stations can transmit data at the same time and can hence lead to collision and data being garbled. Alright, so there are two types of Aloha, pure Aloha and slotted Aloha. Looking at the pure Aloha first. So in pure Aloha, it allows stations to transmit whenever they have data to be sent. Alright, as per it is a random access protocol, so of course it's going to have this functionality that you can send whenever you want. Okay, when a station sends data, it waits for acknowledgement. If the acknowledgement doesn't come within the allotted time, then stations wait for a random amount of time called back of time and resend the data. So basically what does it means is that suppose you sent a data. Now you're not receiving the acknowledgement for that particular data. Okay, there are two things you can do. Either you can wait for, like, you have to wait in between the gap, right, while sending the data and waiting for the acknowledgement. There is a gap, so what that gap is going to be, it could be consistent, that is you're waiting for the same gap each and every time. Now if there is a collision happening, that collision is going to happen so as it was happening, right, the same procedure is going to be repeated over and over. So that definitely is not a smart move. However, if you are waiting for a random period of time before retransmitting that data, then other computers also waiting for a random period of time to retransmit the data. Hence, your random times can't be same. There's quite less probability that they are going to be same. So this decreases the probability of collision to a great extent. Alright, this back of time, waiting for a random period of time before retransmitting the data, if you didn't receive an acknowledgement for the previous data that you sent. Alright, hope you get that. Since different stations wait for different amount of time, the probability of further collision decreases. Of course it does. The throughput of pure Aloha is maximized when frames are of uniform length. Of course it is maximized. Why? Because look, if suppose I am sending a frame of fixed length, that is, it is going to take a fixed amount of time, right? Now I sent a frame and suppose there was no collision and everything went pretty well. Now when I am sending the data in the frame again, another frame is also going to be of the same length, and if the other computer is also doing the same, so the possibility of collision decreases here. However, if they are of different length, then it might be that suppose my frame was of shorter length and the other person's frame was also of shorter length. They passed without any problem. Now if we are waiting for the same time, as of course there was no collision, so we won't be doing any back off. So now we are again sending the data, and this time my frame is my frame's length is longer than it was before. if the other person is still having the smaller length, or he may also be using the longer length. It doesn't matter if my length is longer and they collide with each other. Okay, this is the problem in it. So if you are using uniform frames, then of course this problem can be sorted to quite a it can be sorted a little bit, and the throughput is of course maximized at that time. Whenever two frames try to occupy the channel at the same time, there will be a collision and both will be garbled. Of course it will be. Now this is a very important point. If you look at it, if the first bit of frame overlaps with just the last bit of a frame that is almost finished, but both frames will still be totally destroyed and both will have to be retransmitted later. What does this mean? Just look at this demonstration. Look, B is being transmitted at time t. Okay, it was transmitted at this time. Now just after TFR, suppose this frame is just reached the time t now. Okay, it was first transmitted at t minus TFR. TFR is the time of this frame. Okay, so what TFR time of a frame means? Suppose if I sent a frame at 1 second and it took and by the time was 10 seconds, the entire frame was on the channel. So it basically took 10 seconds to be on the channel for the entire frame. So the time of the frame becomes 10 seconds, right? So at time t minus 10 seconds, okay, so it's just imaginary. I'm just saying that t minus TFR, suppose, let it be any time, a frame was dispatched. Got that? Now at time t, another frame got dispatched. It could be that this frame's TFR could be different than this one's. So suppose it was long or whatever the reason were. If they are going to even touch each other, look, this frame is just ending, right? But this frame was beginning at time t. At time t, this frame was ending, this frame was beginning. They both touched each other and destroyed. Okay, now they are garbled. They have to be retransmitted again. Same is the case here. Okay, this is what this point states. Okay, so these are some of the formulas regarding this, like vulnerable time of pure Aloha, throughput, maximum throughput. Okay, now looking at slotted Aloha, it was basically developed just to improve the efficiency of pure Aloha, as the chances for collision in pure Aloha are high. Okay, the time of the shared channel is divided into discrete time intervals called slots. Now this is the big difference between slotted Aloha and pure Aloha. Basically, in pure Aloha, you were allowed to send data whenever you wish. However, in this, you have particular slots, like from 1 second to 4 second is a slot. Then the next slot will be like from 6 second to suppose 10 second. So you have this type of slots. Okay, just imagine you have to send data. Okay, so you are waiting for your slot. You have to send your data. You have to dispatch your frame in the beginning of the slot. If you are unable to, or unfortunately you weren't able to send the frame or dispatch the frame in the beginning of this slot, then you have to wait for another slot, another turn. Okay, you cannot send your frame or data in between the slot. Once the beginning is passed, then the entire slot is passed for you. You cannot send data in that slot anymore. Okay, sending of data is allowed only in the beginning of the slots. This is what I say. If a station misses out the allowed time, it must wait for the next slot. This reduces probability of collision. Of course it does. Now this is the vulnerable time, the throughput and maximal throughput of slotted Aloha. You can see the difference here. Vulnerable time is is actually half of the vulnerable time that was in slotted Aloha, in pure Aloha I mean. Look at it, it was 2 into TFR, like this time included. This time was the vulnerable time where the collision can occur anywhere. However, in here, just the TFR is the time. This is the vulnerable time where the collision can happen. Alright, hope you got that. Now this is the difference between pure Aloha and slotted Aloha. Any station can transmit the data at any time. Any station can transmit data at any time slot. The time is continuous and not globally synchronized. However, here the time is discrete and globally synchronized. Vulnerable time in which collision may occur is this, and in it, that is TFR, almost not exactly the half of it. Probability of successful transmission of data is this. Here, probability of successful transmission of data packet is this. Okay, maximum efficiency, and it is 8.4% here. Here it is just double, 36.8%. Okay, advantages it is that pure Aloha is pretty simple to implicate. However, in slotted Aloha, it reduces the number of collisions to half and doubles the efficiency of pure Aloha. Now, looking at CSMA, carrier sense multiple access. Okay, so basically this protocol CSMA stands for, first of all, carrier sense protocol. Okay, now to minimize the chance of collision and therefore increase the performance, the CSMA method was developed. Principle of CSMA is sense before transmit, or listen before you talk. Okay, this listen before talk is just an analogy to understand this one. Now, just remember these two terms. Carrier busy means transmission is taking place. Carrier idle means no transmission occurring, no transmission currently taking place. The possibility of collision still exists because of propagation delay. A station may sense the medium that this medium is free and find it's ideal, only because the first bit sent by another station has not yet been received. Now, what does this point means? Let me take you to the browser. Okay, now suppose this particular computer sends this channel to be free. This particular computer has to send its frame to this computer. Now, this computer sensed the channel and found it free, that is idle. However, this computer already sent a frame to this computer. However, the frame that this computer sent was on the way. It was over here somewhere. It didn't reach this computer yet. However, because this frame didn't reach this computer yet, it assumed that the frame is idle and I am able to send my data now. So what it did, as expected, it sent the data. When it came on this medium, it suddenly arrived here. Of course, it's not certain for this computer, but it was already going. This process has already taken place. However, this computer wasn't able to detect it. So here the collision will take place and both of the data frames are going to be destroyed. Okay, so this is what this point basically means. This point, the possibility of collision still exists. Okay, that is why the possibility still exists even before when you are sensing if the channel is free or not. Now, type of CSMA. 1. Persistent CSMA, P. Persistent CSMA, non-persistent CSMA, O. Persistent CSMA, CSMA CD, that is collision detection, CSMA CA, that is collision avoidance. Now, what 1 persistent CSMA is, basically in these points it is written that what you're going to do in 1 persistent CSMA is that you basically are going to, first of all, before sending the data, the station first listens to the channel to see if anyone else is transmitting the data at the moment. If the channel is idle, the station transmits the frame. If busy, then it senses the transmission medium continuously until it becomes idle. Okay, this is basically what CSMA does. We all know that. The thing is that in this, why it is called one persistent CSMA is because it sends the data with the probability of 1. So suppose it found out that this medium is free now. I am able to transmit my data. So what it is going to do, it is going to immediately send its data with the probability of 1. Probability of 1 means it is absolutely going to send the data. It is certain that it is going to send the data. And another specialty of this one persistent CSMA is that it continuously senses the channel. Even if it is busy, still it's going to continuously sense the channel that did it got free, did it get free, did it get free now, did it get free now, like this. Okay, so this is what it's written over here. The propagation delay has an important effect on performance of the protocol. Of course it does. As I already showed you in demonstration on the browser. So the propagation delay, if the propagation delay suppose is longer, the longer the propagation delay, the more important the effect becomes. Like if you have to wait longer, you have, like, let me show you. So if I go here, look, suppose these lengths are pretty long. Now the propagation delay is also going to be long, right? Now suppose, because if this propagation delay was going to less than it, if it was going to send something, then it immediately could be was able to reach to this point. Hence this computer would have been able to sense it. However, if the propagation delay is too long, then it will wait for a time, but this is also going to take a little bit. And since it is going to take a little bit, then this computer will be sensed. By the time it will be sensing that there is no data being transmitted over this medium. So this is the reason, if the propagation delay is long, the possibility of collision increases. However, if the propagation delay is small, the possibility of collision decreases. Okay, coming back to our notes. So this was basically about one persistent CSMA. Now what is non-persistent CSMA? It is basically the same, just the difference here is that I told you earlier, in one persistent CSMA you are continuously going to scan that whether this channel got free or not. Is this channel idle for me? Suppose in non-persistent CSMA, what happens is, if it finds out that this channel is not idle, then it's going to stop, and it is going to check that channel again after a random period of time. Okay, before sending, a station senses this channel. If no one else is sending the station, okay, if no one else is sending, the station begins doing so itself. However, if the channel is already in use, the station does not continually sense it for the purpose of seizing it immediately upon detecting the end of the previous transmission. Okay, instead it waits. That is purpose of immediately transmitting. Instead, it waits a random period of time and then repeats the algorithm consequently. Okay, consequently, this algorithm leads to a better channel utilization, but longer delays than one persistent CSM. That is pretty much certain. P persistent CSMA. It applies to slotted channels. Okay, when a station becomes ready. Now what does it mean is basically that, suppose there are slotted channels, right? You know that what are slotted channels? We just talked about that. So what this P persistent does is, it is going to when its slot comes, first of all it's going to wait patiently, as we do in the slotted channel system. When our slot comes, So then we will be ready to transmit. Okay, what a station become ready to transcend, it senses the channel. If it is ideal, it transmits with the probability P. Now this is the change here, it will be transmitting with the probability of P. So this the probability that this frame is going to be sent is P, and 1 minus P, that is Q. There you go, Q is equals to 1 minus P. Q is the probability that it won't be sent. So this is the case here. Okay, if that slot is also idle, it either transmits or differs again with the probability of P and Q. It might send with the probability of, there's a probability of P that it can send. There's a probability P that it will send, and there is a probability Q that it won't send. Okay. The process is repeated until either the frame has been transmitted or another station has begun transmitting. So if another sort of another station begin transmitting, that it won't be sending its own frame now. Okay. In the later case, the unlucky station acts as if there had been a collision. That is, it waits a random time and starts again. If the station initially senses the channel busy, it waits until the next slot and applies the above algorithm. This was P persistent CSMA. Now O persistent CSMA, each node is assigned a transmission order by a supervisor node. So basically there will be a supervisory node, and that will be assigning that this is your transmission order. Alright. So this was all for today, guys. I hope you enjoyed this session, and if you did, please make sure to subscribe the channel and press the like button. Thank you for watching.